Welcome everyone to another Understanding Deep Learning seminar. Today, Guy will talk to us about the Catapult phase of neural network training. Guy is a staff research scientist in Google and leads a research team focused on taking a scientific approach to advancing the field of deep learning. His recent research focuses on applying ideas from theoretical physics to understanding the training dynamics of large neural networks. Before becoming interested in the science of deep learning, Guy worked on high-energy theoretical physics as a postdoctoral fellow at the Institute for Advanced Study in Princeton and Stanford University. He obtained his PhD in physics from Weizmann Institute of Science in 2014. Guy, please take it away.
Thank you. Thanks so much for the invitation. So let me start with a bit of motivation for this work. The underlying motivation is that we'd like to find a useful theory of deep learning. And what I mean by useful is this should be a theory that both explains the different phenomena that we see in deep learning in practice, but it should also be able to make predictions and useful predictions about how should we better tune these networks to perform the task. So the theory should show us the path forward to making further improvements in these methods. And in particular, there are a few questions that I'm going to highlight that we'd like a theory of deep learning to be able to answer, and we'll try to touch on some of these questions in the talk. So the first question, which has really been driving a lot of the research in deep learning theory, is the question of why do large networks generalize well to unseen data? And this is sometimes called the generalization puzzle. It's essentially the question of, let's say we take a network that's large enough to memorize all the training data that it sees. So with enough training, it gets zero error on the training data. We then go and show it some unseen data, and we find that the performance in many cases is very good. And so the model does not just overfit to the training data, it actually learns something, even though it has the capacity to overfit. And the question is, why is that the case? Why does the network not just memorize the training data? So that's one high-level question. Then there are other more detailed questions. So for example, we know that in practice, training deep learning models, when training these models, it's a good idea to start with large learning rates, start training with large learning rates, and then decay the learning rate as training progresses. And we can ask why is that generally a good idea? Another empirical observation that's been made is that there is a correlation between the local curvature in the loss landscape that gradient descent finds and model performance. So in particular, low curvature minima, flat minima, tend to perform better than sharp minima. And this was shown by Kaskar et al. In 2016 when they considered training with different batch sizes, and has been further corroborated since in other empirical studies. And so we can ask, why does this correlation between curvature and performance show up? And finally, we have some anecdotal evidence that there is something interesting going on in the initial part of training. It seems that in the early part of training, gradient descent takes us from the initialization point down to something we might describe as a basin in the loss landscape, and this happens fairly quickly. And then we spend most of the training time exploring this basin. This is a very vague description, the way I've described it, but we have evidence that this is actually the case. And we'd like to understand better what's going on in the initial part of training, because it seems that there's something, at least from a loss landscape perspective, there's something dramatic going on there. And in this talk, we will consider an example, something that's controllable in theory, but it's also connected to practice, where we can try to address some of these questions and come up with answers. The main paper I'll focus on is the first one here, with my collaborators shown at the bottom, and I will also touch on a couple of other papers during the talk. But the main reference for this talk is the first paper on the catapult effect. Okay, so let me start with a theoretical background that we'll build on in this talk. So we're going to focus on a regime of deep learning called wide neural networks. So let me explain what that means. So in deep learning, what we call depth is the number of layers we have in the network, and we can consider deep networks which have more hidden layers than others. There is another interesting limit that we can consider, and that is the wide network limit. So the width of the network is, or the width of a layer is the number of neurons in that layer. And when we say that we want to make the network wide, what we mean by that is we take the architecture, we take the number of layers, we keep those fixed, the activations fixed, and so on. And we just take the number of neurons in a hidden layer to be very large. That's how we make the network wide. And there are two basic reasons for doing that. One is that practically speaking, making networks wider tends to improve performance. So it has empirical benefits. Making networks deeper does not always improve performance, but making them wider quite generally, at least on vision tasks, makes performance better. Of course, we can't make them as wide as we like because of computational limitations, but at least aspirationally, it's a good idea to make them wider. And the other reason is that making networks very wide sometimes can lead to theoretical control over what's happening. So it's quite difficult to understand the training dynamics and inference dynamics of networks with finite width in a general deep learning setting. But it turns out that if we push the width all the way to infinity, then there are theoretical simplifications that occur. And if you've seen Joshua Saul-Dickstein's talk on this, I think he covered a lot of what we understand about large width networks from a theoretical perspective. In this talk, I'm going to focus on, or we're going to build on one particular result that has to do with theoretical control over wide networks, which goes under the name of the neural tangent kernel. And this is something that was discovered in 2018. And I'll summarize that result now. It's a theorem that says that if you take your deep network, you keep the number of layers fixed, and you make the network infinitely wide. And furthermore, you train it with gradient flow, which means train it in the limit where the learning rate goes to 0. So we're training it in sort of continuous time. Then the network becomes equivalent to a linear model. So essentially, we start with a deep network, a complicated deep network which has nonlinearities in it and so on, which is not a linear model. But once we take this limit and we train with gradient flow, then actually the training dynamics become equivalent to a linear model, become equivalent to a convex optimization problem about which we know a lot. And let me give a bit of intuition for why this is the case. I'm not going to show the proof of the theorem, of course, but just to give a hint of or some intuition for why this comes about. So there's a detail here which I did not mention, which is the network needs to be properly normalized. The weights need to be properly normalized for this to happen. But essentially what happens is, let's say we take our network function f. So f is the network function, w are the weights, and x is the input. What we can do is that we can expand, you can do a Taylor expansion around the weights at initialization. So W naught here are the weights at initialization, and we make a Taylor expansion. So we have the first term, which is just the network value at initialization. Then we have the first gradient term, and then we have higher order terms. And the point is that if we take the infinite width limit and we start training the network, essentially what happens is that the weights don't move much away from their initial values all the way during training. So there are more and more weights because we're making the width larger, but the weights are not moving much, or each individual weight at least is not moving much away from its initial value. And this effectively means that we can drop this quadratic term in the Taylor expansion. And so in the limit, the infinite width limit, we have a good approximation to the network, which is just these first two terms here. And the first term is just a constant. It just depends on what the weights were at initialization. And the second term, you notice, is a linear model term because there's this gradient term here, which are essentially behaves like some random features. Those do not change during training because they're set at initialization. And then that's dotted against this dynamic part, W minus W naught, which does change during training, but this is just a linear dependence on these shifted weights. And so this is roughly why the model becomes linear during training, or behaves as a linear model during training. Another way to understand this and to make a bit of progress is by using Feynman diagrams, which is a technique that we adapted from physics after neural tangent kernel came out to try and understand better what's going on. And so those allow us to those tools allow us to extend these results beyond gradient flow, prove them to also for some cases of gradient descent, and also go beyond the infinite width limit and actually compute perturbative corrections to these dynamics. So that's just a comment on other things that you can follow up on for neural tangent kernel, but that's not going to be our focus here. Okay, so we have this result where if we make the network wide enough and we train it in a certain way, then deep learning sort of boils down to linear model training, which we know a lot about. So that sounds excellent, because it means that now we for the cases where the theorem works, we have a lot more understanding of what's going on. Linear model training is something we understand very well. So that is a step toward a theory of deep learning. Suddenly everything becomes clear and under control, and we can start making predictions and so on. But pretty quickly it became clear that there is a paradox, which I'll call the performance gap paradox. And I want to describe this paradox. It's a paradox between empirical results and theoretical results. And so there are two observations to be made. One is, we've already mentioned that wider networks typically perform better. And I'm mentioning here that when they're over-parameterized, that is when they have enough capacity to memorize all the training data. And here, this is an example, I think one of the first results on this from 2017, which shows what happens when you train networks with more and more hidden units, which is you get by increasing the width. So you can see the training loss improves until it goes to, the training error improves until it goes to 0, at which point we've memorized all the training data. And the test loss also improves and actually keeps improving, even though we are memorizing all the data. Making the model bigger and bigger still gets us to better and better performance. So that is one observation. Wider is better. That is the observation. The second observation that people made after the neural tangent kernel, the NTK result came out, is that they said, well, if we can go to infinite width and get a linear model, that means that we can train the model directly at infinite width. So we cannot instantiate a network with infinitely many neurons. But since we understand what the model is at infinite width, we understand the kernel that controls the model at infinite width, that's the neural tangent kernel, we can just forget about the neural network. We can just directly train the linear model that we find at infinite width. So effectively, we're training an infinite width network, even though we don't actually have a neural network in there at any point. So that is to say, using this theoretical result, we can actually skip all the way to infinite width and train directly there. And the results, which were, here I'm showing one example of these results, but they were fairly consistent, is that the performance you get by doing that is not as good as the performance you get by training an ordinary finite width network. So this is an example from a paper by Aurora et al. From 2019. This is an example on convolutional networks with an architecture detail called gap. That's not really important for this talk, but the main thing to note here are these two columns, CNN gap and CNTK gap. So CNN gap is training an ordinary convolutional network on CFAR10, and CNTK gap is doing this trick of saying, let's take the CNN gap architecture, jump straight to infinite width, assume there's a linear model there, and train that linear model and see what the performance is. So it's like the infinite width version of this network. And you see that the performance is significantly worse when we do that. And so this is the paradox. On the one hand, when we empirically, we see that when we increase the width, performance gets better. On the other hand, when we jump straight to infinite width, performance drops. And the question is, why is that the case? So one possibility, for example, is maybe we didn't increase the width enough. Maybe if we keep increasing the width, performance will just suddenly get worse at some point, and we'll converge to the infinite width result. That was an option that was kind of on the table, I won't go into it too much, but using those Feynman diagram tools we had, we were kind of able to rule out that option. And so there has to be something else going on. What's going on when we increase the width, and why does the theorem why does the infinite width network not give us excellent results? And that is the question we'll address in this talk in one scenario. Okay, so to understand this, we have to go back to doing some experiments and looking at experimental data that try to probe this question of what happens to the performance as we increase the width. And this is a plot showing a set of experiments. So x-axis here is the learning rate, and y-axis is the batch size. And every point on this plot is an experiment where we train a network using this learning rate and batch size. We're actually training two networks in each point here. We're training an ordinary fully connected network on MNIST, or a subset of MNIST, and we're training the linearized version of that model. So we're training the linear model that we would get if we took the width to be very large. And the color at each point is the comparison of the predictions made by these two models, by the ordinary network and by the linear network predicted by the theorem that we would get at large width. And the ordinary network is fairly large width, so we can say it's approaching the infinite width regime. And so basically what this is saying is that if there is good agreement between the network that we train in practice and the linear model, if there is good agreement between the experiment and theory, then the color here will be dark. So dark color means there's good agreement with the theory. Bright color means there's bad agreement. So the linear model that we train and the full network that we train make completely different predictions. Okay, so we see this region here on the left, which is dark, where the predictions from the neural tangent kernel theory work well, and we see the bright yellow region where the predictions are not good at all. The points here on the right with the X's, those are points where the model did not manage to train. The full network did not manage to train. And you can see this happens if we take the learning rate to be too large, then the training diverges and we can't train, which is to be expected. And the last thing to note on this plot, which is kind of the most interesting point on this plot, is the blue X. The blue X is where we get the best performance out of all of these experiments on the network that we trained. And notice that the blue X is straight in the middle of the region where the theory breaks down and does not correctly describe the training dynamics of the network. Okay, so to summarize the results, just the empirical results that we're seeing, we're sweeping over these two hyperparameters, learning rate and batch size. We see that there's a region where the theory works, and that is roughly the small learning rate region. And we see that as we cross a threshold, as we cross a kind of what looks like a critical value of learning rates, suddenly the theory kind of abruptly breaks down. We can still train the network just fine, and in fact, we get the best performance there, but the theory doesn't work. And if we keep cranking up the learning rate, then we get divergences, and the model stops training. And just to connect it to the theorem that I mentioned before, the actual theory we're building on, that theory is guaranteed to work for gradient flow that is in the limit of small learning rate. So that's going all the way to the left here. So that's where the theorem is guaranteed to hold, and that is indeed where we find good agreement. Okay, so the goal now will be to try and understand why this is happening. Why do we have this this rapid change from theory working to theory not working, and to try to build up the theory behind this effect. And so the first thing I want to say about this at a high level is, so I come from a physics background, and when I look at a picture like this, it really reminds me of the sort of phase diagrams that we see in physics. So in physics, a phase diagram of a model is something that shows the qualitative behavior of a model as we change certain parameters. So for example, here's the phase diagram for water. We can change the temperature, we can change the pressure, and there are like large regions where the qualitative behavior is the same. So it's either a gas or it's a solid if it's ice or liquid, but then there are these critical lines or critical points where there is an abrupt change in behavior, even though we change the parameters by very little. So of course, this happens when we boil water. As we cross a critical temperature, the water goes from liquid to gas and so on. And this looks very similar to me, at least when I look at this, it looks very similar to a physical phase diagram in the sense that there are large regions of similar behavior and then abrupt changes across small changes in the hyperparameters. And indeed, we'll see that this is not just a surface level similarity. This system actually, the neural network actually exhibits phase transitions in the same sense that we see in physics. And what we'll end up with is a picture where we have 3 distinct phases. Or at least right now, it looks like there are 3 distinct phases. There's a small learning rate phase where we have good theoretical understanding, but the performance is not optimal. We have the large learning rate phase where the performance is good, but we don't have a theoretical understanding. So kind of mirroring what we saw, what people see in practice. And finally, a phase where things just diverge and the model cannot train. Okay, let's look at a bit more empirical results showing in a bit more detail what's going on when we run these experiments. So the first thing I want to show is, as we train one of these networks, what does the training loss look like as a function of training time? And here, it's important that we're measuring the training loss every single step. And we'll see that there's something interesting going on. It's not like once per epoch like we usually do. Here, we're measuring it every single step. And so we see that when we do it at these larger learning rates where there's deviation from theory, we see that the training loss initially diverges, goes up pretty high before it comes down again and training does continue and eventually converge to a good minimum. Each point here, again, is just a single step. So over the course of like 5-6 steps, we see something that looks like a divergence in the training loss, and then it turns around and works just fine. This does not happen in the low learning rates like we see here at the bottom. So that's one curious effect that we'll try to explain that's going on when we train with these large learning rates. The second effect shows up when we measure the curvature. So we already mentioned that curvature is, well, some measure of curvature is correlated with good performance. We know that curvature is a kind of a basic observable that's interesting to measure when training networks. And here what we're doing is we're sweeping over learning rates. This is not time now. These are learning rates. We're training the network for a bit, and then we're plotting the curvature. Here, the curvature means the maximum eigenvalue of the Hessian. So just a local measure of how curved the landscape is. And what we see is that at small learning rates, the curvature is fairly constant. It doesn't change with learning rates. And then there is a critical point beyond which the curvature starts dropping. So as we crank up the learning rate, we train a network with a larger learning rate, we end up somewhere which has a lower curvature. And so we see, again, some kind of transition that's happening here around a critical point. That's another kind of signature of this effect that we'd like to understand. All right, so we discussed the paradox between the empirical results and theory, and we've discussed a simple example, a fully connected network trained on MNIST, where we kind of see these different phases of learning as a function of learning rate. And we've seen a couple of signatures. The loss blows up, the curvature changes. And now we'd like to collect all these things together and find a model, a simple toy model, that exhibits as many of these effects as we can. And then once we understand what's going on with this model, we'll use it to make some predictions, and then we'll go and test those predictions. We'll go back to ordinary large convolutional networks and test whether those predictions are actually corroborated. So in the next part of the talk, I'll describe the theoretical model. It's an incredibly simple model. It's going to be just a two-layer network. It's going to be a linear two-layer network, so there are not going to be any nonlinearities. But we'll see that this model is rich enough to exhibit all these different phases and to kind of explain all these effects that we're seeing in a very simple setting. The one thing we'll do to this model is we'll make it very wide, because that is kind of where we see the interesting stuff happening. Okay, so let me describe the model. Again, it's a very, very simple model. We have 1D, so for the purpose of this talk, I'll focus on the simplest version, which is a model with 1D inputs, 1D real input, 1D real output, and a single hidden layer in the middle with n neurons, and no nonlinearities. So these neurons are all linear neurons, and so the model itself is linear. We also are going to train this model on just a single training sample. Just one training sample, x equals 1. The input is x equal 1, and the target is y equals 0. Again, for the purpose of this talk, we're going to keep it as simple as possible. We can complicate things a little bit, as we do in the paper, so we can actually do d-dimensional inputs. We can have a general training set. These things don't matter much for the dynamics. Here, to hopefully make things as clear as possible, we'll do the simplest version so that we can really track all the dynamics and see what's going on. Okay, so this is the network function. U and V are the weight vectors in this case, because we have 1D inputs and 1D outputs. So U and V are vectors, the weight vectors that we're going to train. And this is the function. And I've dropped here the input x, because x is just 1. So we're going to always just evaluate this function on the same input x, so it doesn't even appear here. And this is the network function. We're normalizing by square root of n. And we're initializing the U and V weights with variance 1 to be Gaussian variables. That is the same normalization as is used in the NTK paper. So that's called NTK normalization. For the loss, we're going to use mean squared error loss. The experiments I've shown before are also for mean squared error loss. That is going to be important. All these observations I'm making here in this talk apply to mean squared error loss. They don't apply to cross-entropy. Cross-entropy loss is a very different story. So the loss is simply f squared over 2. We have just one training sample. This is the loss we're going to train on. All right. So this is the setting. We're going to do gradient descent on these parameters with this loss. And we're going to see what happens. So here are the gradient descent equations in their full form. We're updating the U and V weights. These are there are 2n equations here, and even though the model is very simple and the loss is very simple, these are complicated equations. We don't know how to solve them in full, of course. These are coupled nonlinear equations, and so we have to use some tricks to make progress and understand what's going on in the training dynamics of this network. And the training dynamics are what we have to study if we want to compare theory and experiment after we've trained the model, obviously. So really, we want to study these as a function. We want to study these equations as a function of the learning rate. And so what we're going to do is we're going to make a simplification, which is we're going to study this problem not in weight space, like we just wrote it down, but instead in function space. And this is a common trick that's proven very useful when studying wide networks. We're going to look at the way the function evolves under gradient descent. So we're still updating the weights using gradient descent as before, but we're not tracking the individual weights per se. We're tracking how the function itself evolves. And so here, the first equation shows this is the update equation under gradient descent of the network function. And so we have this first term here, a multiplicative term involving the function. And then we have a term that I didn't write down explicitly, but it's a term that's suppressed by 1 over the width. We're going to be taking the width to be very large, and so this term is going to be suppressed. We can do the analysis with this term, but it's not going to be important. There's a new variable that shows up here in this first equation, which I call h. H is the curvature. Here, h is the trace of the Hessian of the loss function, so a measure of the curvature of the loss landscape. It's also just given by the sum of the squared norms of the u and v weights. So this is such a simple system that different concepts kind of become the same. The curvature is the same as the L2 norm of the weight. So there's a very simple formula in this case for this h, but this is what it is. And so because h shows up, we don't yet have a complete set of equations. We have to write down the update equation for h as well. And this turns out to be the full update equation for h. We have h itself, and then we have a term that looks like it's being suppressed by 1 over the width, but will actually be important. So I wrote it here down explicitly. And the nice thing, the thing that all the simplicity bought us, the fact that we don't have any nonlinearities and that the loss is simple and so on, is that this is the complete set of equations. We can describe if we care about the function dynamics, we can describe it just using the function and the curvature. So instead of 2n equations, we're now down to just 2 equations. So these are still non-trivial equations, but we can actually analyze them and see what's going on. So this is now, we've reduced the problem to a set of 2 gradient descent equations, and now we're going to analyze the dynamics of these equations as a function of the one parameter that we have, the learning rate, and taking the width to be large. So again, the learning rate here is eta, and the width is n. And the thing we'd like to see is, we'd like to see this behavior where at small learning rates, or we hope to see the behavior at small learning rates, we have the theory holds, and the model is behaving like a linear model during training, and then across a certain threshold, we get this new large learning rate behavior. So let's see how that works. So the first thing we're going to do, since we care about large width, is that we're going to take the width to infinity. So we're going to take n to infinity and see what happens. And once we do that, the equations reduce to this simple set of equations. So first, the curvature does not get updated. The curvature stays constant throughout training at infinite width. And the function receives, the function itself receives these updates. And these updates, if you work out what happens to and with h being constant here, so h is now the curvature, which is constant. If you work out the update equations for a linear model, you'll find that they are the same. You have a constant curvature, which is the curvature given by the Hessian, which is constant for linear models with MSE loss. And this is the update equation for the function. So we've essentially recovered, in this case, the NTK result. It's like a special case of the NTK result. We took the width to infinity, and we find that the model behaves like a linear model. However, we got a bit more, because it's not just the gradient flow that this is happening. This is also happening at finite learning rates. Because this is still the update equation. Even for a finite learning rate, it's still the update equation for a linear model. So essentially, we have something that's bouncing around inside a quadratic bowl. And now we can understand that we can do convergence analysis for this case. And we see that given some initial curvature h naught, we see that this will converge as long as the learning rate is smaller than 2 over the curvature. So we can go, let's say, and measure the curvature, and then we know this is going to converge when learning rate is smaller than this number. Okay, and this is the same result as this is a known result from linear models. So there's nothing new here. Okay, so far so good. Everything is here. We're training with a learning rate beyond a certain threshold. We find that the model is linear, and this agrees with the NTK result. Okay, what happens when we cross this threshold? So if we do that, if we train with a larger learning rate, the linear model is going to diverge. You see this factor here, which is constant, is going to be bigger than 1 in absolute value. And so as we're training, the network function is going to explode exponentially fast in the training step. And it's just going to converge. So again, because the loss here is just f squared, the minimum is at f equals 0. So here the function is exploding and it's not converging. However, now we have to go back to the full description. So remember, we got this description by taking the width to infinity, and we dropped some terms in these equations. But once the function starts exploding, these terms might become important, and they will become important. So we're going to bring them back to the analysis, and we see what happens. So strictly at infinite width, we're going to get a divergence, but we have to go back to the full equations that we have at finite width and see what's going on. Okay. So we're back with the full set of equations, and now we see what's going on here. So let's look at this term, the update term, which is suppressed by 1 over the width, the update term to the curvature. We see that here, as long as the learning rate is not too large, so as long as we're in this particular window of learning rates, this factor here is going to be negative, which means that the curvature is going to get negative corrections. As the function blows up, it's just going to get bigger and bigger negative corrections. So you can see that if we're in this window of learning rates, the function is going to be blowing up during training, but the curvature is going to go down. Once the curvature is small enough, this term is not going to lead to an explosion anymore. It's actually going to become smaller than 1 in absolute value, and it's going to cause the function to converge. So there are two things happening at once. The function is blowing up, the curvature is going down. Once the curvature is low enough, the function is not going to blow up anymore. It's going to converge. This is happening as long as we're in this window. So the linear model would diverge, but the full neural network is actually able to converge, even though it looks like it's diverging initially. And this is happening very quickly because this function is blowing up exponentially fast. And so this whole thing is going to be over within log of n steps. So for typical n, for typical widths, let's say 1,000, it's going to be over in a matter of a few steps, a very quick process. Here's an illustration of what these equations are doing when we're training the network with a large learning rate. So this is showing a slice of the loss landscape of this problem. The y-axis here is the curvature, or also the L2 squared norms of these parameters, and the x-axis is the weight correlation. It's essentially the angle between the two vectors, u and v, the two weight vectors. And the color here is the loss. And so we start with this initial point, and at large learning rate, we start diverging. The loss is increasing because the function is blowing up, but the curvature is going down. We're going down the y-axis. These things are happening at once or simultaneously. And once the curvature is small enough, then we see that we have convergence and we end up at a nice minimum. We also notice that we end up in a minimum with a lower curvature than the initial one. So this is an illustration of these dynamics. I see there's a question. You said this is, let me read it. You said this is valid for MSE and cross-entropy, is a whole other story. Do the results also work for mean absolute error? Are there any results for cross-entropy loss? We don't yet have results for cross-entropy loss, I can say. I mean, we have initial results, but the story is much more complicated. And the catapult, there is a catapult effect there, but it's not as clearly connected with the best performance anymore, it seems. So that is why it's more murky. We really want to connect first, the dynamics are much more complicated, but also it's the connection with the performance is much less clear. So I don't have much to say about that. And the question, do results also work for mean absolute error? I don't know. We haven't checked that, so I don't know the answer to that. Okay, and the next question is, how do learning rate schedules interact with the catapult effect? So that's a great question, and I'm gonna address that a bit later in the talk. You'll see all the results on that. The short answer is that this is a very quick effect, so it's really just the initial learning rate that matters. Once this effect is over, you can decay the learning rate and you kind of reap the benefits of this. We're calling this the catapult effect. You're going to reap the benefits of the catapult effect. So learning rate schedules do not ruin this. It's really just the initial learning rate that's important. Okay, awesome. Okay, so we have a model. Let's look at some more detailed dynamics of this model and compare it also with the results we've seen before. So when we look at the training loss, a function of step, we see the same thing we saw early on. So when we train with these large learning rates, we see the loss blowing up and then converging. And now we understand why. It's because of this is the part where function is growing exponentially and curvature is decreasing. And then once curvature is low enough, we have convergence. So we understand why this is happening now from the theory. And we can also look at the curvature versus step size. We see that when we train with small learning rates, we have the linear model behavior where the curvature is constant. And when we train with large learning rates, we see this decrease in the curvature due to the catapult effect. So again, the same as the results we've seen before, the toy model is capturing these results. So we've seen this before for a fully connected network with ReLU, like an ordinary network. Now we see the same results for the toy model. Okay. And finally, we have, just to complete the analysis of the phases, we have the divergent phase. So if we train with the learning rate that's too large, that's above 4/h, then this additive term to the curvature is positive. The curvature is going to just keep growing, and the function is going to keep exploding, and everything is going to diverge. So here, none of the models converges. Okay. I want to make a short comment about how this is like a phase transition in physics, because I mentioned that before, and how this is not just like a surface level similarity. So here, when I say the phase transition, I mean in particular crossing this threshold where the learning rate is smaller than 2 over the curvature versus larger than 2 over the curvature. That's like the critical thing that separates the two regimes. And I want to let me just mention quickly a couple of ways in which this is really like a phase transition in physics. So one is that we know from physics that when there is a phase transition, it's often accompanied by a breakdown in perturbative expansion, in Taylor expansion. So what I mean by that is we have one regime where we can do a Taylor expansion in our parameter, and if we have enough orders in this expansion, that's going to be a good approximation to what to whatever we want to measure, like let's say to the way the function behaves during training. But once we cross the critical rate, the perturbative expansion breaks down, the Taylor expansion breaks down, and it doesn't matter how many orders we keep, we're not going to get a good approximation. And this is exactly what's happening here. So as I mentioned, we worked out in a previous paper, we worked out a 1/width perturbative expansion to the training dynamic. So we can have the infinite width term, and then we can have finite width corrections order by order. And turns out that once we set the learning rate beyond the critical rate, because of the fact that the function blows up, every order in this Taylor expansion blows up, and we lose control. We lose computational control. And so this case is actually the same as what we know in physics should happen when we have a phase transition. The other hallmark of phase transitions in physics, or second order phase transitions, is that they exhibit power laws when we are close to the transition. In this case, we also see something like that. We can compute the convergence time of gradient descent. The convergence time goes to infinity when we tune the learning rate to be very close to the phase transition, and it actually goes to infinity as a power law, and we can compute and measure the exponent that controls this power law. So very similar to what you would like, these sort of plots you could see when you measure various properties of magnets as you change their temperature, and we've seen many plots like this in physics, and so we can also have these we also see these power laws for this simple neural network. All right, so that's on the analogy. Let me summarize the predictions that we get from this toy model, and then we'll go and we'll compare them against ordinary experiments. So we're talking about MSE loss. With MSE loss, we have this regime of learning rates, large learning rates, where ordinary networks train, but the neural tangent kernel result does not hold even at very large width. And I'm going to write this down like this. So learning rate is, for this regime, is going to be between 2/h0 and some maximal learning rate. The maximal learning rate turns out to not be completely universal. It depends a bit on the architecture. For the deep linear model, it was 4/h. For all the ReLU networks that we tried, we find that it's roughly 12/h. We can't reproduce the number 12 theoretically, so this is kind of a phenomenological result or empirical result somewhat, but it seems fairly consistent in our experiments. And h0 here is going to be the maximal Hessian eigenvalue that we can measure at initialization. So if you have your favorite network, you can go and measure the eigenvalue at initialization. It's a pretty cheap measurement, and then this tells you the range of learning rates where you can see the catapult effect, where you have this large learning rate behavior. And by catapult effect, I mean that in this regime, the loss is going to grow to be order of the width. It's going to grow to be very large within a short number of steps, within log n steps. And if you measure it every step, you're going to see this. The other thing that happens is that the final curvature is going to be lower than the initial curvature, which is not really the case when you use a small learning rate. And now making a jump, we know that there is a correlation between curvature and optimal performance. We see that with large learning rates, we expect to get lower curvature, and in particular in this regime. And so we can speculate that this is the regime we want to train networks in, because maybe we'll get the best performance there just based on curvature. So that remains to be seen. We have to run the experiments, because that's not something that theory gives us. This is now a connection we make using other results that we have. So perhaps this is the optimal regime to be training networks in when we use MSE loss. All right, and so again, let me just summarize. When do all these results are valid? When are these results valid? So the main assumption here is that it's MSE loss. This does not apply. Cross-entropy, again, has different behavior. It does apply not just for linear activations, but for different activations as well, for ReLU and for tanh. The only caveat here is what is the actual maximal learning rate, which is an empirical result. You can do convolutional networks, dense, we'll see this in a minute. You can use batch norm, you can use SGD. These results all still seem to hold. The two things that break these results are, again, cross-entropy loss, it's not going to work, and momentum does have different behavior as well. If you use momentum, then the transitions between the phases are not as sharp. Basically, it smooths out these transitions that we see between the phases. All right. Okay, so now let's see some empirical results and see how these predictions hold up in practice. So this we've already seen. It's a fully connected network with ReLU trained on MNIST, and we see the catapult effect here. When we train with small learning rates, the loss goes down, and when we train with large learning rates, we still converge, but we see this loss exploding at first. We see the catapult. And we've already seen this as well. Curvature with low learning rates stays more or less the same. And curvature beyond this critical 2 over, now we can say this line is the 2 over h, or 2 over lambda critical learning rate. This is our prediction. Beyond this line, we see this significant drop in curvature. And this black line here, dashed black line, is the 12 over lambda line, which is where we expect the maximal learning rate to be. And indeed, beyond this point, we see divergence. So this is all good. This works and matches our predictions for this ReLU network. Now let's go to some more modern architectures, let's say. This is a wide ResNet, so like a modern convolutional architecture. We train this on CFAR10, and we see with mean squared error loss, and we see, again, the same behavior. So small learning rates, the training loss is going to go down. This is hard to see in this plot, but there's no jumping around or anything. It just nicely converges. When we train with large learning rates, we see this explosion. We see the catapult effect in the training loss. And again, I want to stress, if you want to see this in your experiments, you really have to measure it every step. So each point here is just a single step. So this is really kind of interesting, I think, that you take an ordinary, like, off-the-shelf network, you tune the learning rate to a reasonable value. You see, these are not like very large value, just 0.25, 0.24 is like standard ordinary learning rates we would train these network with. And you see this weird effect where the loss grows dramatically before. But if you just ignore this, everything is fine. You get a very well-performing network. But since we know where to look now, we can see the catapult effect here, and we sort of also understand why it's not a harmful effect. And again, looking at curvature versus learning rate, we see the same behavior. As long as we're below the 2 over lambda critical learning rate, curvature is more or less constant. Once we're above, curvature drops dramatically. And the maximal learning rate here, you can see the agreement between the black dashed line, which is our like empirical prediction, and the red area where we have divergence. We see that this captures the maximal learning rate of this network pretty well. All right. And the last comparison, and maybe the most interesting comparison, is how well do these networks perform in the catapult phase? So is it true that it's a good idea to train networks in this narrow window of learning rates? Is that where we get the best performance? So there are some caveats when we do these experiments. The caveats are that we need to be careful when designing these experiments to make sure that the comparison is fair. And there are two effects I want to point out here, because we're going to be comparing performance across different learning rates. And there are confounding factors that we need to control for. So there are two things that happen when we turn the learning rate, when there are two sort of trivial effects that happen when we take the learning rate larger that we want to control for. The first is that larger learning rates mean that we're taking just bigger gradient descent steps. We could say that it might be performing just as well as smaller. I mean, smaller learning rates might be just as good, except that the larger learning rates are going to just get to the minimum faster, right? So that's not an interesting effect. We want to control for that, and we do that by whenever we use a smaller number of training steps, a smaller learning rate, we increase the number of training steps proportionally, so that it's not just a matter of, oh yeah, we trained with a very small learning rate and it just didn't move away from its initial point. That's not interesting. So we boost the smaller learning rates by giving them more time to train, which in an ordinary setup, if all we care about is our computational budget, we're not going to do that. We're just going to choose the best learning rate. But it's just that scientifically, to have a fair comparison, I don't want to say, yeah, the large learning rates won, which means that the catapult effect is better, where in fact it's just the fact that the small learning rates didn't have a chance. So scientifically speaking, we want to control for that. Practically speaking, it's just that this is yet another reason why large learning rates is better. But that's not the effect we're interested in here. And the second effect, which goes in the other direction, is the fact that toward the end of training, when we're in this basin and we're sloshing around the minimum, larger learning rates lead to more noise. It makes it harder to get closer to the actual minimum, which works, and that's an advantage that the small learning rates have. And so we're going to control for that by, during the end of training, we're going to decay the learning rate. And no matter what initial learning rate we started with, we're always going to decay to the same small learning rate so that we have the same noise at the end of training. Because again, that's an effect that's completely separate from the catapult effect. So we have these two controls in these experiments, which are hopefully enough to isolate the effect we actually care about. Right? So here, results, again, on a wide ResNet modern network, trained on CFAR10. This is test accuracy at the end as a function of the learning rate. The two dashed lines are our predictions for the window at which the catapult effect happens. And the line I want to focus on here is the red line. That is where we have all the controls. So proportional number of training steps and eventual decay of learning rate to the same value. And we see that once we put all these controls in place, the best performance happens within this predicted window. So that's one result. And again, as I mentioned, if what you actually care about is just to get the best performance for a given budget, then that tilts it even more in favor of using these larger learning rates, just because of this effect that the small learning rates don't stand a chance. They don't even get to where they want to get to. So from a practical perspective, this would be the plot to look at. Okay, so let me summarize. So we've seen that for mean squared error, when we look at gradient descent dynamics of wide networks, they fall into three distinct learning rate phases. In a small learning rate phase, we have excellent theoretical control. We know that in the infinite width limit, seemingly for any learning rate within that window, the model will become will behave like a linear model, but we typically don't get the best performance there. Then we have a sharp transition at this critical learning rate 2/h, which we can compute separately for every network. We have a sharp transition to the large learning rate regime where we observe the catapult effect. The loss goes up very dramatically and then goes down. And we've seen why this happens, at least in a toy model that captures these effects. And the practical outcome of all of this is if you train your network with the assumptions we've made here, then you can go and measure the performance, the curvature, at initialization. Again, it's a pretty cheap measurement, and these numbers will give a good hint as to where the optimal learning rate is going to be. So that's all I had. Thanks a lot for listening. I see there's one question I did not answer. Do you have any recommendations for someone with a computer science background interested in learning the underlying physics to enter this research topic? So from what I've seen so far, it's hard to predict kind of where the points of contact with physics are going to be. So I mentioned that we found one point of contact with Feynman diagrams, which is like a tool from particle physics. Here we see that there's some connection with phase transitions, which is that's not high energy physics. That's like, that's a much more broad field in physics. I would say if you're interested in this direction, then I think reading about phase diagrams, phase transitions, second order phase transitions, the Landau model, ferromagnets, the Ising model, maybe starting with the Ising model would be the best place to start. Those are kind of the entry points to understanding phase transitions better. So if you're interested in this particular connection with physics, I would say, then learning about phase transitions, and especially starting with the Ising model, which is pretty approachable, would be a good starting point, I would say. Yeah. Okay, I see another question on YouTube. Do I take the Hessian of the initialized weights regardless of whether the neural network is initialized random or Gur-Ari uniform? That is correct. The initialization method does not matter for this purpose. We don't rely on that. Whatever you initialize your weights, you just take the Hessian, measure the top eigenvalue, and that's the number we care about. Yes, because the reason is that we don't. So in many of the wide network works, we take expectation values over all the possible initializations, and then it does help. Well, first of all, it does matter how we initialize just to do that calculation, and typically it helps to have Gaussian initialization. But in this work, we don't take any averages over. We don't take expectation values over initialization. So that's why the initialization method doesn't matter in this case. Okay, see another question. A common approach when training neural networks is to set a scheduler to keep decreasing the learning rate when the model stops improving. Do you think by doing that in a complex loss landscape, we're increasing the chances of overfitting? I mean, I would say it's really task dependent. I mean, if what you care about, just empirically from what we see, if what you care about is the final validation performance, then decaying the learning rate is generally a good idea. Like that should be the default approach, because it just generally leads to better performance. If your question is whether this increases the generalization gap, I actually don't think it will, because even that's not going to happen, because in an overparameterized setting, the training error is 0 anyway, and we do see an improvement when we're decaying the learning rate and the validation error. So that means even the generalization gap is just getting smaller. So yeah, I would say no, I don't think it's increasing the chance of overfitting. But that's a question that, if you have a particular case in mind, you can do the experiment and see. I'm just saying, generally speaking, we have not seen that this increases the chance of overfitting.
Okay. I think those were all the questions. So Thank you very much, Guy. Yeah.
Great, thank you.
Oh, wait, so there's let's get this to be the final question.
Another question, okay. How do I define the phase transition in the neural network? Looking by learning rate and size of the batch. I see, yes, good. Okay, because that's right. Just go back. That's right, because the first, yeah, that's a good question. So the first results I've shown, we scanned over both the learning rate and the batch size, and the question is, and so the transition is not happening just at a point. We have two parameters now. There's a whole line of phase transitions here, or sorry, a line of phase transitions that are happening. This is more complicated, of course, because the theoretical results we've seen we could say are all for full batch gradient descent. I should have mentioned that, but like in the toy model, in the toy model, we only analyzed full batch gradient descent, and so we kind of analyzed this point here at the top. And crossing the line in this direction when the batch size is large. Once you look at smaller batch sizes, you have to account for SGD noise, and it becomes, the equations we looked at were deterministic because it's full batch, so you have to account for the stochasticity of SGD in that case, and it becomes more complicated. So I don't have a full answer for that. Thankfully, we can see from this experiment that the effect of batch size is pretty mild. And so when we've done, for example, the experiments on wide ResNet, it was not full batch, it was SGD, but we see that the predictions from the full batch still hold pretty well. And this is because the SGD noise is actually a pretty mild effect. So I don't have a full answer for, I can't give you like a theoretical explanation of the shape of this line, but we do see that it's not as significant as changing the learning rate.
Okay, so again, thank you very much, Kai. And for all the attendants, hope to see you again next week on Samuel's lecture on signal propagation and dynamical isometry in deep neural networks.
Thank you.